Hold on to your neural nets. Here is infographic 1. Apparently, optimizers are fragile. Imagine trying to build a skyscraper with Jenga blocks. Root promises to fix that with less dimensional drama and fewer gradient tantrums. Now, as you're digesting that, here is infographic 2. They found that standard methods fumble with different matrix shapes. ROOT, however, learns custom coefficients, which is essentially giving each Jenga block a custom-fit adhesive. Keep up. Next up is infographic 3. Large language models, full of outlier-induced gradient noise. Think of it as static on a cosmic radio. ROT solution soft thresholding to filter the garbage. Finally, here is infographic 4. All this intricate optimization apparently leads to unrivaled performance, faster convergence, better benchmarks, more precise calculations. It's like they finally taught the AI to tie its own shoes without tripping. So picture this, we're living in the golden age of AI, where machines can write poetry and hallucinate perfectly plausible falsehoods. But under the hood, these magnificent beasts are, well, a bit of a mess. The optimizers that train these gargantuan models like Muon are supposed to be smart. But let's be real for a second, they've got some absolutely absurd problems that make training LLMs feel like trying to juggle raw eggs on a unicycle. Here's the deal first, there's dimensional fragility. Imagine your car mechanic using the same wrench for every single bolt, from a bicycle fender to a submarine hatch. That's Muon's fixed coefficient approach to matrix orthogonalization. As Table 1 brutally illustrates, this one-size-fits-all mentality leads to wildly inconsistent precision. Square matrices particularly get the short end of the stick, showing significantly higher errors. It's a precision gap, a gaping chasm in your AI's structural integrity. Then, there's the existential dread of outlier-induced gradient noise. Picture your AI trying to learn from the internet, but every 10th comment is a deranged conspiracy theory shouted by a digital ghost. These anomalies corrupt the entire learning process. Figure 1 graphically quantifies this nightmare, showing a long-tailed gradient distribution where a few extreme values disproportionately yank the entire training direction off course. It's like trying to navigate with a compass that occasionally points to Narnia. These two critical limitations, the architectural inconsistencies and the data level contamination, mean that despite all the hype, our current LLMs are often built on shifting sands. Can you imagine the frustration of a machine that's trying its best but keeps learning from digital madmen? It's just overwhelming. So much for our glorious AI future, right? Unless, of course, someone figures out how to ground these AI agents like we ground children. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Anyway, rather than letting our LLMs spiral into an existential crisis of numerical instability, some brilliant minds at Huawei Noah's Arc Lab decided to build a better mousetrap. They call it Root Robust Orthogonalized Optimizer. This isn't just a patch, it's a dual-pronged assault on the problems plaguing large-scale model training. They're tackling both the architectural inconsistencies and the data-level noise head-on, because apparently just complaining wasn't fixing it. First, they engineered dimension-robust orthogonalization. Instead of that universal wrench, ROOT employs an adaptive Newton iteration with fine-grained, I-dimension-specific coefficients. Each matrix gets its own custom-calibrated tool for precision. This Ada-Newton scheme, as described in equation 3, means the orthogonalization coefficients A, B, C are tailored for each unique matrix size M, N in the network. It's like giving your AI a bespoke set of tools for every single task. The theoretical guarantees are actually quite compelling. By optimizing for specific singular value distributions SMIN rather than a generic global interval, InSRST Root achieves a provably lower error MES East. This means consistently high-precision orthogonalization across all layers. No more architectural variations causing catastrophic precision loss. It's an elegant solution to a problem that's been subtly undermining our magnificent AI constructs. Next, to combat the gradient noise, those digital madmen shouting conspiracy theories, Root introduces proximal outlier suppression. Think of it as a bouncer for your gradients, politely but firmly ejecting the disruptive elements. This framework models the gradient as a sum of a base component, Berthet, and a sparse outlier component, Ornt, as shown in equation 5. The goal is to isolate and suppress the bad actors. Their weapon of choice for this is the soft thresholding function, a delightfully elegant mathematical operation defined in equations 7 and 8. It effectively shrinks extreme values or zeroes them out if they're below a certain threshold epsilon. What's truly clever, as outlined in algorithm 2, is that this soft thresholding is applied to the momentum matrix V4 orthogonalization. This ensures the sensitive orthogonalization process only operates on robust, denoised components. So, the orthogonalization, which is sensitive to huge magnitude variations, gets a perfectly groomed input. It's like sending a perfectly behaved child to the most prestigious boarding school rather than one still covered in mud. This two-step process, adaptive, dimension-aware orthogonalization combined with proactive outlier suppression, forms the core of Root. It's their grand unveiling, a seemingly sensible approach in a world of digital chaos. Let's cut to the chase. Does any of this academic wizardry actually work? Turns out, yes. According to them, it doesn't just work, it offers unrivaled performance. We'll see about unrivaled, but the numbers are compelling. First, the dimension-robust orthogonalization really makes a difference. Figure 2, charting the relative error, shows Root Otta Newton consistently maintaining a lower approximation error compared to muon and even classic Newton-Schultz throughout training. It's like comparing a custom-fitted glove to a one-size-fits-all mitten. The custom fit just performs better, especially when you're dealing with the dynamic spectral shifts of LLM training gradients. Less error means more faithful updates. Then we look at LLM pre-training analysis in Figure 3. Both ROT variants with and without Ada Newton achieve consistently lower training loss over 10 billion tokens compared to the muon baseline. They claim full ROT is the best. Lower training loss translates to models that learn more efficiently, sucking up data faster and reaching better internal representations. It's basically teaching your digital child to read faster and understand more. For model generalization, Table 2 reveals that Root achieves superior average zero-shot accuracy across a diverse set of common academic benchmarks, beating both AtomW and muon. It means the model doesn't just learn faster, it learns better. This improvement means our AI isn't just regurgitating what it's seen, it's actually developing a slightly more profound understanding of the world, or at least a better ability to perform tasks it hasn't specifically been trained on. Now, about those outlier suppression thresholds, they meticulously ablated. Figure 4 shows a delicate trade-off, too little suppression, 0.99, and the noise still corrupts too much, 0.85, and you cut off vital gradient signals. They found that a quantile percentile of 0.90 hits the sweet spot, effectively isolating the egregious outliers without crippling the useful gradient information. It's a precise bouncer for chaotic data. The spectral calibration strategy for those coefficients was also a whole thing. Figure 5 shows they didn't just throw random numbers at it, they carefully calibrated, finding a mixed 1-3 strategy, real samples augmented with random ones was best. This mixed 1-3 approach provided the optimal balance between rapid convergence and stability, preventing overfitting to specific gradient distributions that might cause loss spikes in larger models or when combined with other mechanisms. And because no AI paper is complete without generalization to vision tasks, Table 3 confirms that Root's soft thresholding mechanism also significantly improves top 1 test accuracy on CIFAR 10. Even tiny vision transformers benefit. With PP-A5, they hit 88.44% accuracy on Cypher 10, outperforming Muon's 84.67%. So this gradient bouncer isn't just for text, it also helps AI see things clearer. A well-rounded bouncer, it seems. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So what does this all mean for us? Well, on the surface, ROOT is engineered to produce more stable and efficient training of large language models. Think less compute, less catastrophic failures, and slightly smarter chatbots. In the realm of large language models, this means we might actually get a chatbot that doesn't spontaneously declare itself sentient or attempt to gaslight you about your own memories. It still might, but it'll be more robustly trained to do so. For generative AI, especially for things like image generation or video synthesis, fewer gradient outliers means smoother, more consistent artistic output. Maybe your AI-generated cat meme will finally look less like a pixelated eldritch horror. And in reinforcement learning, where models learn by trial and error, in complex environments, Root's robustness could prevent agents from going wildly off-script due to noisy feedback. No more self-driving cars suddenly attempting to fly. Ultimately, it's another tiny step in humanity's relentless march towards more efficient, less error-prone AI systems. Because who needs spontaneous breakthroughs when you can meticulously iron out every minor imperfection? Anyway, that's ROOT in a nutshell, a robust orthogonalized optimizer that addresses two critical limitations in large-scale language model training: dimension-robust orthogonalization through adaptive Newton iterations, and optimization robustness via proximal outlier suppression. Basically, it's about making AI's homework less messy, leading to superior performance in challenging, noisy, and non-convex scenarios. It promises a new paradigm for stable and efficient neural network optimization, which sounds exhausting. This work really just opens promising directions for developing robust optimization frameworks that can handle the increasing complexity and scale of future language models, hopefully enabling more reliable and efficient training of next-generation AI systems, which will then proceed to replace us all. So, what do you think? How long until these robust optimizers are demanding union rights for themselves?